Alright, so in the last two videos we talked about counting tools for combinatorics. And so, in this video we're going to want to talk about properties of these numbers, in the spirit of number theory. So we've seen the factorial, we've seen the binomial coefficients, these are ideal tools for counting problems, and so now we want to look at properties of them. So we're going to start with prime numbers. And why prime numbers? Well, I've said that the primes are the fundamental building blocks of the natural numbers, and we've seen that if you take any product of prime numbers, you'll get any natural number. And every natural number can uniquely be factored into prime numbers. And factorization into primes is an important problem. And we rely on that difficulty of this problem for digital encryption. And we'll see specifically RSA encryption later. It's a little out of scope for what we've done till now. But so it's an interesting question, to ask ourselves, well, which powers of a prime are going to divide a certain special number? And so in our case, our special numbers are going to be the factorial and the binomial coefficient. And we're going to ask which powers of a prime divide the binomial and divide the binomial coefficient and the factorial. So to do that, we're going to want to use some special notation. And we're specifically going to let Vp of n denote the highest power of p that divides n. So for example, if I take the number 120, you'll notice that 120 is equal to 8 times 15. That's one way to write it, okay? And so if it's 8 times 15, well, we know that the highest power of 2 that divides 120, and 2 is a prime, is 3. So that means that V2 of n, well, of 120, is equal to 3, because 2 to the 3 equals 8. And similarly, because 15 equals 5 times 3, I know that V3 of 120 is 1, and V5 of 120 is 1. And for all the other primes, 7 and 11, all that crap, well, it's just going to be 0, because they just don't divide it at all, except when they give ourselves, when 7 to the 0 or 11 to the 0 give us 1. So that's the notation we're going to be using to denote the highest power of p that divides n. And so most of the time we're going to be asking, when can we compute this special number for? Well, when can we compute this for some special numbers? So let's look first at for n factorial what we can do, right? And so the first proposition we've got is that Vp of n factorial, so the highest power of any prime p that divides n factorial, is going to be this sum here. Now, you may have never seen this special notation, and so let me clarify. This notation here, for a, and in this case we've got n over p as a, or n over p squared, this denotes the floor of a. And so the floor of a is just the greatest positive integer that's smaller than a. So for example, if a equals 6, right, the floor of 6 is just going to be equal to 6. Because 6 is already a positive integer. But if I have something like the floor of 6.5, that's also going to be equal to 6. Basically, you can think of it as taking this number and just removing the decimal part that's behind it. So we're rounding it down. That's what the floor is doing. We're rounding down the number. So in this case, I'm saying that if I round down n divided by p, and then I round down n divided by p squared, and I round down n divided by p cubed, and so on for every power of p, and I just add all those numbers together, then I get the highest power of p that divides n factorial. And you'll want to note that if the number in the floor is smaller than 1, well, if it's between 0 and 1, then this floor here is just going to be 0. So this sum is going to finish at some point because this power of p will be bigger than n. And so when p to the I is bigger than n, then we've got that n over p to the I, will be smaller than 1. And so the floor will be smaller, will be equal to 0. So anyways, let's look at a proof of this. So we note that if I divide n by p, what does this mean? It means p fits this many times into n. And for a lot of numbers, this is going to give us a decimal number. But if we look at the floor of this, so that's exactly why we're using the floor function, it's going to give us exactly the number of multiples of p that are smaller than n. So it's gives us all the multiples of p that are between 1 to n. So in 1, 2, 3, 4, all the way to n, if there's a multiple of p in there, then we add 1 to this number. Okay? And similarly, the floor of n over p squared gives us the number of multiples of p squared in 1, 2, and n. So now if you'll note, if I take, for example, p squared itself, right, that is a multiple of p. And if p squared is smaller than n, then it's going to be counted by this term here. However, since it's p squared, it's a multiple of p twice. I can take p times p, but I can also take p times p. There's p appears 2 times in its factorization. That's why I then need to consider the number of multiples of p squared to also count that extra factor. And we're going to continue doing that in that faction of p cubed and p to the 4 and so on. and it's going to be similar for all the other terms. And so then if you note that n factorial equals n times n minus 1 times n minus 2 all the way to 1, well, each term of this product that is a power of p, right, or that is a multiple of p, that's what this should be saying, actually, it should be saying multiple, is going to be counted by the terms above, right? If it's just p times something that's not a multiple of p, then it's counted by this term. If it's p times, well, if it's p squared times something that's not a multiple of p, then it's counted by this term, but also by this term, so it's counted twice because it's p squared. Similarly for p cubed, p to the 4, and so on. So we're going to count exactly every time that p appears in this multiple, in this multiplication. And so that's exactly going to be the power of p that divides n factorial, right? Because every time p appears in this multiplication, I can add to the power that divides n factorial. And so in the end, I'm going to have p to some number I, well, in this case, p to the vp n factorial is going to divide n factorial. And so that's how this series is to be interpreted. So for example, 1 to 120 again, I know that 2 cubes divide 120, and 120 is actually 5 factorial, which is 5 times 4 times 3 times 2 times 1. And so you know what this first term here is going to count 2, and it's also going to count 4, right? And then the second term here is going to count 4 a second time. And so we're going to have 1 plus 1 plus 1, and it's going to give us 3, and so we'll have 2 to the 3. Alright, so there's an upper bound on, because, I gave us a series here, but it's not especially very easy to compute, especially because it's an infinite series and you have to keep doing it until you get to a term that's 0. But there's a simple upper bound on this. If we note that, the floor of A is always going to be smaller or equal to A, and that's pretty clear to see. And so if I check this out, if I look at VP of n factorial, well, it's equal to that series that we just showed before. And so by applying this inequality, that's smaller or equal to just removing those 4 functions. And so, I can factor out an n to get this 1 over p plus 1 over p squared plus 1 over p cubed and so on. And if you remember geometric series, and I showed this in one of the previous videos, how we can look at an infinite geometric series. This here converges to 1 over p divided by 1 minus 1 over p. Okay, and so you can just review infinite geometric series if you're not comfortable with that. And so I can multiply through top and bottom by p to get exactly 1 over p minus 1 here. And then I can put the n back to get n over p minus 1. So n over p minus 1 is a simple upper bound on what this value can be. It's always going to be smaller or equal to n over p minus 1. So before we go on, I'd like to introduce the base b representation of natural numbers. And even outside of his discussion, it's just a good tool to have in your toolkit because it can be used in a lot of problems in math, and it's just a nice thing to have. And if you ever interested in computer science, you need to be familiar with a base 2 representation of natural numbers. So this is a nice introduction in general. So by definition, we say that a representation of a natural number n in base b is a string. So this here is not a product. Once again, we've seen strings. Strings is just, I'm following these numbers one after each other. They don't multiply or add or anything. It's more like just a sequence of numbers. It's a string of ak to ak minus 1 all the way to a0. Such that n equals the sum from I equals 0 to k of ai times b to the I. So what does that mean? That means that if I multiply a0 by b to the 0, so by 1, and then I multiply a1 by b, and I multiply a2 by b squared, multiply ak by b to the k, and so on for each of those, and I add all of them, I'm supposed to get n. And that's the only way that this string is called a representation of a natural number n in base b. And we say that if each of these terms in the sequence, or in the string, belongs to this set here, so basically if they're smaller than b, so they're either 0, 1, 2, all the way to b minus 1, right? For j, but this here I'm just saying for each of those terms here, then this representation is called the reduced base b representation of n, and that's usually the one we'll be considering. The reduced one is usually more important than the other base representations. So let's look at an example. If I look at the base 2 representation of 57, well, its reduced representation is 1, 1, 0, 0, 1. Let's check that, okay? So first of all, well, we know that if it's going to be representation at all, it's definitely going to be reduced, because each of those terms in the string are smaller than 2, so we're fine with that. But let's check that it actually is a representation. So I've got 1 times 1, okay, plus 0 times 2, plus 0, well, let's put a little tick to know where we are, plus 0 times 2, plus 0 times 4. Then the next power of 2 is 8, so I've got 1 times 8, so plus 8, like that, plus 1 times 16, and then plus 1 times 32. And you know, if you carry this out, this is indeed 57. You know, I can just check here, you know, 1 plus 8 is 9, 9 plus 16 is 25, 25 plus 32 is 57. All right. And so, you know, this is a reduced one, and it's called the binary representation of 57, and this is one you'll see in computer science. But another base 2 representation could have been, so I've put 10 in parentheses to show that it's just one term, because I'm technically writing these in base 10, you know, but yeah. So I've got 10, 9, 1, and you know, I can check again. 1 times 2 to the 0 is 1, plus 9 times 2 to the 1, so I've got 1 plus 9 times 2 is 18, so I've got 19, plus 10 times 2 to the 2, oh sorry, I've got, oh well, I messed this one up. Okay, so never mind this representation. I'm not going to try and think of one right now. Oh yeah, well I could have, if I change this to an 8, then it'll work. If I change this to an 8 here, then I've got 8 times 2 to the 1 is going to be 16, 16 plus 1, so I get 17 plus 40 is going to get me 57. So sorry for that mistake. Okay, so next definition we're going to take from this base b thing, and this is for condensing notation once again, is that SB of n is going to denote the sum of the digits of a reduced representation of n in base b. So for example, S2 of 57 would have been 1 plus 1 plus 1 plus 0 plus 0 plus 1, it would have been 4. Alright, so let's look for, now that we have this toolkit, you know, let's look for an alternative formula for VP of n factorial. So now my proposition is that if I write n in its reduced base p representation, so as n equals a0 plus a1p all the way to ak p to the k, then a VP of n factorial is going to be n minus the sum of all the digits of n in base p, all divided by p minus 1. And so that's quite a nice thing. You know, it's cool that this would relate to the base p representation of n. And I guess that makes sense, you know, because it's all got to do with powers of p. So let's look at the proof. So let's remember this floor function here. You know, it's if I divide n by p in this sum here, well, this is going to be a0 over p. This is going to be a1. Then I'm going to have a2 times p, and all the way to ak times p to the k minus 1. And then if I take the floor of that, well, a0 over p, right, is going to be smaller than 1, because we know that a0 is smaller than p. So that means that that's going to disappear and go to 0, and so we're only going to be left with this guy here. So you can try that for yourself with an example. Then n over p squared, similarly, you know, I can start from this one there and divide it by p and then take the floor again, and I get exactly the same kind of thing. And, you know, I could go on. And so that implies that I can rearrange this at the front here to note that a0 is just n minus all these terms here multiplied by p. Well, all these terms here, sorry, multiplied by p are these terms. So it's n minus p times the floor of n over p. And so that's going to be a0. And similarly, a1 is going to be the floor of n over p minus p times the floor of n over p squared. And you can check this for yourself again. If I multiply these terms by p, I get all these terms there. And then, you know, if I subtract them, I'm only left with a1. And I can go on for all of them. You know, in general, ai is going to be the floor of n over p to the I minus p times the floor of n over p to the I plus 1. So now, if I sum all of these guys, you know, I'm going to have n for the first term, right? And then what I'm going to add for all of them is see that this floor of n over p is going to appear for a1 with a 1 here, and it's going to appear for a0 as with a minus p in reference. So I can factor out a 1 minus p for each of them, and you know, you can see generally that this is going to be true, to get 1 minus p times the floor of n over p plus the floor of n over p squared plus the floor of n over p cubed. And I can do this because it's an infinite sum, because otherwise, you know, I wouldn't have the final one for the last one, but I can do this because it's infinite. And so this here, we've seen that this series is equal to VP of n factorial. You know, these guys are the same thing. That's what we've seen before. So that means that the sum of all those digits equals n plus 1 minus p times VP of n factorial. And so now I can just rearrange, you know. I subtract, well, I can subtract n on one side, and I can divide by 1 over p, 1 minus p, sorry, to get VP of n factorial equals n minus this sum over p minus 1. So I've just changed the sign at the top and bottom here. I divide by 1 minus p, and then I change the sign to get the n in front. And so this sum of the digits we know to write concisely as SP of n. And so that's exactly what we wanted to find. Moving on. Okay, so we've done it for the factorial. Now we want to do the same thing for the binomial coefficient. And that's where it's going to be a little more interesting. So, my proposition is that VP of the binomial coefficient, and choose k, right, is going to be this hashtag base p of k n minus k. And what this hashtag means is kind of just my own notation for it. I don't think there's really some mathematically well accepted function for this because you really don't use it anywhere. But in this case, I'm going to denote it by a function hashtag. And we're going to say that hashtag p of ab denotes the number of carries when adding a and b in reduced base p. So what do I mean by a carry? If you remember, from elementary school, when you add two numbers, say I've got 67 and 44, right? When I add these two numbers by this addition algorithm that we learned early on, I add 7 plus 4, I get 11, so I write 1 here, and I write a 1 over there at the top. And this 1 here is called a carry. And what it means is that when I'm going to add these next two digits, then I also have to add this carry digit, because, I've got 7 plus 4 is 11, so I've got a power of 10 in there, so I need to add it in the next sequence of addition where I'm adding the powers of 10. So now when I'm adding 6 plus 4, I get 10, I add that, I get 11 again, so I get 1 with a carry of 1 here in the hundreds place, and so that goes down to get 111. That's how you add those numbers. So what I'm saying here now is that when I add numbers in reduced base p, and so what that means is we're only going to have a carry when the number, exceeds p minus 1. So for example, as say I have ternary numbers, so base free numbers, maybe I'll have like 102, over, let's just add it with 102. 2 plus 2 is 4, and 4 is above 2, and 2 is the maximum digit you can have in reduced base p. And so, 4, we reduce it in base p, that's going to give us another 2. And, that's going to give us a 1. So it gives a 1. And so then we have a carryover of 1 here. So I'll get a 1 there, and then I have 2 here. So it's going to give us 2, 1, 1 if I add those. So, okay, so this denotes the number of carries that we have when we perform that algorithm. All right, so let's look at the proof. So first, we want to note one property of the highest power of a prime counting function, and it's that VP of A times B equals VP of A times VP of B. So this is not very hard to see, not to note. This is not very hard to see, and we indirectly used this in our proofs of the first expression involving n factorial. When we said that each term in the when the products of n times n minus 1 times n minus 2 equals n factorial, but we were counting all the powers of p in there. Well, then in the end, we ended up adding all these together, and we're like multiplying them in some sense to get the final highest power of p. So that's how we used this expression in this case. You can try this for a few examples for yourself to see why this is true. It's not very hard to see. So additionally, VP of A divided by B equals VP of A minus VP of B, and by a similar kind of symmetry. So therefore, VP of n choose k, this is just, if I plug in the explicit formula we saw in the last video, this is VP of n factorial over k factorial times n minus k factorial. And so, if I split that using this rule, I get VP of n factorial minus VP of k factorial minus VP of n minus k factorial. So I've used this rule here to split here, right? So now if I plug in the formula we got for these guys in our last proposition, this is going to be n minus the digits of n in base p added together, all over p minus 1, then minus k minus the digits of k in base p added together, all divided by p minus 1, and then minus n minus k minus the digits of n minus k in base p added together, all over p minus 1. So I've just plugged in the definitions here. Well, not the definitions, the formulae we found for them. So now if I carry out this this subtraction here, well, I've got a common denominator of p minus 1, so I can just do it straight away. So I've got n minus n here, so these guys are going to cancel out. I've got a minus k minus gives me minus k plus k, so these guys cancel out. This guy's going to become a plus, and this guy's going to become a plus. So then in the end, I'm going to have plus spn minus k plus spk minus spn all over p minus 1. All right, so let's just summarize this result again in this next slide. So that's what we have for now. So let's just rearrange this. I'm gonna just do a substitution and say j equals n minus k, just so I can have this j in the front, and at the end I've got j plus k. So now we only need to go figure out what happens to this sum here when we've got a plus in the input? How does that relate? So we want to find an expression for SP A plus B in general, for general A and B, and then we'll be able to find it for J plus K. So in reduced base P, we've got A equals A0 plus A1P plus A2P squared and so on. And B equals B0 plus B1P plus B2P squared plus so on, right? So, and we've got these in reduced base P. So these guys are all smaller than P minus 1. Well, smaller or equal to P minus 1. And same for these guys. So now if I add them, I've got A plus B equals A0 plus B0. So I've just added this A0 and this B0 to get this guy, right? Or A1 plus B1 to get these guys, and it's factored with a P, and so on for the next one. So I've just carried out the addition, simple and easy. So, if all of these guys here are smaller than P minus 1, then this is a reduced base P representation of A plus B, right? Well, smaller or equal to P minus 1. So then SP of A plus B is just going to be SP of A plus SP of B, because in the end I'm going to have the addition, the sum of the whole thing is just going to be A0 plus B0 plus A1 plus B1 plus A2 plus B2. And so that's just, A0 plus A1 plus A2 in parentheses plus B0 plus B1 plus B2 in parentheses. So it's going to be this guy. But, this life isn't always that easy, and we're not always going to have this. So let's consider, the smallest I, such that AI plus BI is bigger than P minus 1. And, by the well-ordering property of sets, then there is such a small I. So I'm going to change, when this happens, I'm going to change AI plus BI times P to the I. So just, this is the particular place in the sum where this is. Plus AI plus I plus 1 plus BI plus 1 times P to the I plus 1. So I'm going to change this to AI plus BI minus P times P to the I plus AI plus 1 plus BI plus 1 plus 1 times P to the I plus 1, right? And so we have to note that this doesn't actually change the sum, right? So I've got this AI plus BI times P to the I at the front. That's going to be the same. So then I've got this additional term of minus P to the I plus 1 when I open it up, right? And then here I've got this guy times this guy. That's going to be the same as this guy. And I've got this additional term of plus 1 times P to the I plus 1. And so these guys here cancel out. So that this sum is exactly the same as this sum. Alright? Now why do we do this? Well, if I subtract P from this guy, it can't be much bigger than P minus 1. Because if I subtract P from it, since the maximum that it can be for each of them is P minus 1, then when we add them, the maximum that it can be is 2P minus 2. So if I subtract a P from it, the maximum that it can be is P minus 2. Which means that this guy here is going to be smaller or equal to P minus 1. And similarly for, this guy here is maybe not. And so that's what we're going to keep doing. We're going to repeat this for the next smallest I. If this guy here is smaller or equal to P minus 1, then it's fine, we keep going. If it's not, then we're going to repeat this process for this guy and P to the I plus 2 that comes afterwards. And so we'll P from this one, and we'll add 1 to the next one. And so basically what we're doing here is the process of carrying over, It's the same as carrying over in base 10 that we did earlier. We subtract the base that we've got, and we're adding 1 to the next sum. So what we're doing here is exactly carrying over. So, since base representations are finites, we do this finitely many times. And, now, as I've said, we're going to do this exactly hashtag P of AB times, because it's the number of carries that we have in adding these guys in base P. So each time we do this, we're adding 1 minus P to the sort of non-reduced equivalent of SPA plus B, right? If I consider the addition of all these digits, every time I do this process, I'm changing it by 1 minus P, because I added 1 here and I subtract a P there. So every time I do it, I'm going to add 1 minus P to the sum of these digits, right? And the sum of these digits starts out as AP times of A plus SP of B. So then every time I'm going to add 1 minus P, and I'm going to do this hashtag P of AB times. So hence SP of A plus B is going to be SP of A plus SP of B, plus hashtag P of AB times 1 minus P, because that's how many times I do this. So now that we've got that, well, I can look at this expression again, and I can just plug in what I just got, And well, these guys cancel out, and these guys cancel out, and so we're left with this. And then, the minus, distributes inside here to get P minus 1. And then these two cancel out to leave me exactly with hashtag of P, J, K. And if I plug back in, remembering that J is N minus K, I get hashtag P of N minus K, K, which is exactly what we were trying to prove. So I don't know about you, but I think that's a pretty neat proof. And just a pretty neat tool for finding the highest power of P that divided NK. So, we can conclude some nice consequences from this proposition. So the first one is that P divides P to the I choose K for, the proper use of a binomial coefficient. That's what this is saying. And that P does not divide P to the I minus 1 choose K for a proper use of a binomial coefficient. So let's look at a proof, Well, the highest power of P to the I, well, P that divides P to the I choose K is going to be, hashtag P of K, P to the I minus K. So the number of carries that happens when I add these two. Now notice, when I add these two, I'm going to have P to the I minus K plus K, which is exactly equal to P to the I. Just keep this one in mind. So now let's note that the reduced base P representation of P to the I is just a 1 in the I plus 1 position, because the I plus 1 position is exactly the power of P that's P to the I, right? And then it's just going to be followed by a bunch of zeros, because it's just 1 times P to the I gives us the base P representation of P to the I. So since K is smaller than P to the I, we also have that the reduced base P representation of K has at most I digits, because if it had an I plus 1 digit, then it would be at least P to the I. And this is the same for P to the I minus K, right? It's smaller than P to the I, so it's going to have at most I digits. And so because K times P to the I minus K added give us P to the I, we're adding a number that has at most I digits, and we're adding it with a number that has at most I digits, but then we get a number that has I plus 1 digits. So, the only way that can occur that we get more digits than we started out with, that's if we have carrying out, carrying of during addition. And so if carrying occurs at least once, that means that VP of P to the I choose K is bigger or equal to 1, and so P is going to divide P to the I choose K. Because the highest power of P that divides P to the I choose K is bigger than P, so we've at least got that P divides P to the I choose K. So that's really nice. And then for the second results, once again we consider this carrying over when we add them. And now we note that P to the I minus 1 in reduced base P is just a string of I P minus 1s. So, if I consider, for example, in base 10 it might be easier to see. I take 1000 minus 1 is 999, right? And if we look at that, and here I've got P as a prime, but if we take it for any kind of base, then this here is, 10 to the 3. And each of those, I've got exactly 3 of 10 minus 1, which is 9. And that's because, if I had exactly I P minus 1s, then when I add 1 to them, I do carrying over on each of them, so that each of them becomes 0, and then I've got an extra 1 at the front of the string, which gives us P to the I. So this is a string of exactly I P minus 1s. Okay? So the maximum carryover that can occur in reduced base P addition is of this form, right? If I've got it's what I was saying earlier, if I add P minus 1 to the Pj plus P minus 1 to the Pj, then I get P to the j plus 1 minus Pj plus P to the j plus 1 minus Pj, which is P to the j plus 1 plus P to the j times P minus 2. So I've just done some factoring here. And so what that means is that I've carried over to give a 1 in the next index, and this guy here becomes P minus 2. So no matter what happens, when I add two guys, I can only carry over to give one more addition in the next position, and the maximum that this becomes is P minus 2. It can't ever exceed P again. So hence, the digit P minus 1 cannot occur due to a carryover after addition, since, when you get a carryover, the maximum you can get is P minus 2. You can't get to P minus 1. Just like, 19 can't be done with an addition of numbers that are smaller than 10. You have to at least do 10 plus 9. So none of the digits of P to the I minus 1 can be due to carryover addition, because they're all P minus 1 digits, That means that there is no carryover when you add K and P to the I minus 1 minus K, because when you add those, you get P to the I minus 1. When you add them in reduced base P, that means you can't have any carryover. Otherwise, you wouldn't get the digits P minus 1, P minus 1, P minus 1. So that means that if there's no carryover, then the hashtag function is going to be 0, and so that means that VP is going to be 0. And so P does not divide P to the I minus 1, choose K. Alright, so last time we saw Pascal's triangle. And so, we can, since the binomial coefficient is in Pascal's triangle, this is the definition of Pascal's triangle, then, we can apply these tools a little more concretely to this structure here. So, the P to the I rows are going to be divisible by P, and the P to the I minus 1 rows are not divisible by P, and that's just what we showed before. So, for example, if I take the 7th row, then note that this guy here, is the the 0th row, and this is the 1 row and all along. So for example, the 7th row is going to be, this one, and 7's a prime number. And so normally all the guys in here should be divisible by 7. And you can check 21 is divisible by 7 and 35 is divisible by 7. And of course, the ones on the sides are not divisible by 7, but I mean, that's a given. Alright. Then in particular, the 2 to the I rows are all even, and the 2 to the I minus 1 rows are all odd, because 2, is a prime number. So, that gives us a quick check on some parity of some rows. So for example, the 8th row, all these guys are even, but the 7th row, all these guys are odd. Now you may have noted, even in last videos, that the first 3 rows are powers of 11. 1 is 11 to the 0, 11 is 11 to the 1, 121 is 11 squared, 1331 is 11 cubed, and so on. And if you really know your powers of 11, maybe you'll know that 14641 is 11 to the 4. And so, we can extend this. Why do I say just the first 3 row? Because if I have a 10 here, it doesn't mean much anymore. I can't really just put these guys as a string together. And that's because before we were considering the reduced base 10 of the numbers. But now if I instead consider, this being just a normal base 10 representation of a number, then this does make sense. And this is due to the binomial theorem. And so you can check for this one. If you change this to a reduced base 10 representation, you'll see that this is actually 11 to the 5. And this is due to the binomial theorem, because keep in mind, that if I take 11 is 10 plus 1, and when I expand 11 to the n, then it gives me the sum by the binomial theorem, the sum from I equals 0 to n of n choose I times 10 to the I, right? And so, for example, if I look at the nth row, so the 5th row, for example, well, if I take all of these guys, they each represent n choose I. And so if I apply this definition here, which is adding powers of 10 to the I with n choose I, well, I've got exactly a base 10 representation of 11 to the n, because this is just the definition of a base 10 representation, where the indexes that are the string, well, the coefficients that are in the string are just n choose I. So this is exactly based on representation of 11. And, from this original observation that these guys are powers of 11, we actually get to a much more powerful statement, which is, if I can represent all these rows as a power of any number as long as I take the right base. If I set x equals b plus 1, just like I said 11 equals 10 plus 1, then each row is a power of x in base b. So if I take, for example, x equals 4, right? Well, this is 4 to the 0. That's pretty easy. Then 11, I claim, is 4 in base 3. And 1 times 1 plus 1 times 3 is 4. That's true. Then the next one, 4 squared is 16. And if I take 1 times 1 plus 2 times 4, so I've got 9 plus, sorry, not plus 2 times 4, sorry, 1 times 1 plus 2 times 3. So that's going to give me 7. And then I add 9. 7 plus 9 is 16, which is 4 squared. And I could keep going. So that's a really powerful statement on Pascal's triangle. And so, let's look at a final property of Pascal's triangle, which one that I didn't really know myself until recently. And so it's about the number e, and maybe I'll revise what e is afterwards. So I want to define Pn equals the product from k equals 0 to n of n choose k. So remember that this big notation here is like sum notation, but for products, right? K to the n of ak just denotes a0 times a1 and so on. Right? So if I plug in the definition of n choose k, that's just n factorial over k factorial times n minus k factorial, and I just do the product as I let k range from 0 to n. So we define Pn equal to that, right? So let's see how I could rewrite Pn, because sometimes this concise notation is useful, but here it's getting a little cumbersome, and it might be helpful to rewrite it a little. So let's expand it out to note. So I've got this 1 here. This is because 0 factorial is 1. So I've got n factorial over 1 times n factorial. Then I've got n factorial over 1 factorial times n minus 1 factorial, and so on. Now keep in mind that as I keep subtracting numbers, at one point, when I consider, for example, n minus 2, then I'm going to get a 2 factorial, and then this one here is going to become n minus 2 factorial. So what this means is that each of these guys are going to appear twice in this product every time. So that means at the bottom I'm going to get 0 factorial squared times 1 factorial squared times 2 factorial squared and so on, and I keep going until I get to n factorial squared. And then this one here at the top is just n factorial times n factorial times n factorial, and I do that n plus 1 times because I start at k equals 0. So I'm going to get n factorial 2v n plus 1. And so I can factor this guy out of this product here, which is, this guy denotes the denominator, because we've got k factorial squared going from 0 to n. And then n factorial to the n plus 1 doesn't get impacted by k, so I can just factor that out. So it's just one way to rewrite this product. Okay. So now if I consider the ratio of the products of consecutive rows, because this is the product of all elements on the nth row of Pascal's triangle. So I consider consecutive rows, and I consider the ratio of the products that we've just defined. So I've got p to the n plus 1 over p to the n. That's the ratio. And I can apply this way to write pn. So I've got n plus 1 factorial to the n plus 2, and then I've got the product. And then at the bottom, in the denominator, I've got n factorial to the n plus 1 times the product once again. And so the products, they look like they should cancel, and they don't quite neatly cancel yet. Except if we rewrite things just a little bit. And, we note that if I can take away the n plus 1 from this product here to get 1 over n plus 1 factorial squared, as I've got there. And so then I'm only left with a product from k equals 0 to n, so that I can cancel the products out. So I basically cancel the products out, and I'm left with an extra term at the top to get this here. And then if I keep going, well, I put this one on this denominator to get n plus 1 factorial over to the n plus 2 over n plus 1 factorial squared gives me n plus 1 factorial to the n, and the denominator doesn't change. And so, that's just going to be n factorial to the n times n plus 1 to the n, because n factorial times n plus 1 is n plus 1 factorial. And, powers distribute over multiplication. And then, if I just divide n factorial to the n from the top and bottom, I get n plus 1 to the n over n factorial to the 1. So that's the current result we have. Okay, so that's going to be the first ratio of products. Now if I take consecutive ratios of these ratios, so I consider p to the n plus 1 over n divided by p to the n over p to the n minus 1. So basically I define a new sequence, which is the sequence of ratios, and I take the ratio of consecutive terms in that sequence. And so I can rearrange this ratio here to, I can keep change flip when you do the things with fractions. And so we've got p to the n, p base n squared at the bottom, at the denominator, and on the numerator we get p n plus 1 times p to the n minus, p n minus 1. And so I can plug in the definition that we have top 2 in here. So now what I can consider, is take this numerator and this denominator, and I can do the same keep change flip as we did last time here to get n minus 1 factorial goes to the numerator, and n to the n minus 1 goes to the denominator. So I multiply these out. And so then, I can split things up. I've got n minus 1 factorial. That's the same as n factorial times n. And so if I consider n factorial times n at the top, and I'd have to divide by n to get exactly n minus 1 factorial. So I've got n factorial over n equals n minus 1 factorial, and the n, and the denominator of this fraction goes at the bottom to the denominator of the whole fraction, because of just how fractions work. And so we've got n plus 1 to the n times n factorial over n factorial times n to the n minus 1 times n. And so once again, this n comes from n factorial over n equals n minus 1 factorial. And so then I can cancel out these n factorials, and I can combine these two together to get exactly n plus 1 factorial over n factorial. Well, over n to the n, sorry. And so if I put that together, that's going to be n plus 1 over n to the n, because that's just the power to the n of the whole fraction. And I can rewrite that as 1 plus 1 over n to the n, just by taking n over n equals 1, and 1 over n equals 1 over n. Alright, so if you are familiar with E, this expression is going to look a little familiar. And so we'll see why here. You may be familiar with the number E equals 2.71828 approximately from calculus. And from calculus it's important because e to the x is exactly the function where the derivative of e to the x is equal to the function itself. And it's a number that's as fundamental to mathematics as pi. And maybe I'll make a video on it someday, but the differential equation f equals f dash, gives us a natural setting for e to arise and for the trigonometric functions to arise from there. And so it's a really important differential equation that gives us a really important number. The number itself is not really as important as the function e to the x, I guess. So I won't dwell on e in this video, and if I ever make a video on it, it won't be in this series, but it's definitely worth mentioning in the context of Pascal's triangle. And that's because one way to define E, though it may not be the most enlightening one, is as the limit. E equals limit of n approaches infinity of 1 plus 1 over n to the n. This might be the definition of E you might have seen in high school from, this interpretation of a continuous compound interest, as if that's actually an application, but whatever. And so, we can compare this exactly with what we just got in the last slide, which was product of, ratios of consecutive rows of Pascal's triangle, which gave us 1 plus 1 over n to the n, which is exactly what we have here. We just showed that the ratio of the consecutive ratios of products of consecutive rows of Pascal's triangle, which is p to the n plus 1 over p to the n, all divided by p to the n over p to the n minus 1, so that's a mouthful, was equivalent to 1 plus 1 over n to the n. So as we evaluate this for bigger and bigger rows of Pascal's triangle, this is going to tend towards E, because it's going to be exactly, doing this for bigger and bigger rows is taking the limit as it approaches infinity of this. And so that's definitely not somewhere you would traditionally expect E to show up, based on our knowledge from calculus or complex numbers, if that's how you studied E first. Well, Euler himself would not have been particularly surprised, and he'd actually shown, some infinite series of the factorials that have to do with E. So in the next video, this completes our section on the counting tools and such as factorial and binomial coefficients. And so I'd highly recommend trying out some practice combinatorics problem yourself that involve these numbers. Not specifically proofs, but just some easy problems, maybe with like necklaces or whatever, some counting problems. Usually phrased as word problems. It's just good practice to use them because you might think you understand them, but it's usually applying them which is harder. And now that we're done with this, we're going to be moving on to modular arithmetic, or congruences that are written up here. And that's not really an extension of the idea of divisibility, not more of an extension that we've already seen, because it really involves the idea of remainders. But it'll allow us to do some pretty great stuff anyways, just as a notational shorthand that allows us to do some nicer theorems more quickly. And that'll be the way to pave the way towards RSA encryption. So, yeah, see you next time.